look at this picture. Yesterday I looked at it. It actually is a very nice setup. You have all the ingredients for the future, and also work in relation to modeling and simulation, which is what I have been doing in the entire my career, basically about 30 years. Today I'm going to talk about a topic is on multi-scale simulation. And this simulation, I changed the title a little bit. I was planning only talking about the coupling between the molecular dynamics with the so-called smooth particle hydrodynamics technique. But then after I submitted my abstract, and my students still carry on with their work. And then once we found some results, the results wasn't that so fantastic. So that basically says that we have to move further. And moving further is basically on the quantum mechanics of simulation. So today, I'm going to talk about, in general, computational methodology, and then talking about the coupling work that we have done so far, and then what we are going to do to move forward to solve some of the problems that we have found in our research work. The work I'm going to present is in collaboration with RPI. We had actually a joint research program, not as big as this one, but it's still multi-institutional type of work. So I'm the PI. I originally from China, so it's difficult for people to actually pronounce my name. So people always call me GR. Okay, so you just call me GR. I will be very happy if you do so. And Guang Yu is my student. He's a PhD student, currently working at the University of Cincinatti. He's on his third year now. So he's going to complete the entire work, otherwise he may not be able to get his PhD. And these two gentlemen are from Applied, and they are very good at the quantum mechanics modeling based on so-called density function theory. If I talk too fast today, this is my website. So you can always, this is my email, this is my website. You can always go there and take a look to see what type of work I have been doing so far. And if you have questions, just send me an email, then we can discuss further. I'm going to use these very busy slides to just let you know what I have been going through in the past 30 years. And how that is going to help me to solve the problem, to modeling so-called very specific materials we call explosives. Okay. For explosive, what happens is that when the materials get shocked and get ignited, then you start to, we call it detonation. Okay. Once detonation happens, and it explodes, so the whole thing happens very, very fast. Okay. The reaction part, the detonation part, is on the nanosecond, this kind of time frame. And then once the explosive detonated, exploded, then we need to know at the terminal effect, I mean, you put the explosive here after detonation. I want to see how the building actually behaves. Okay. So once you come to the discussion of the response of the building, then it's a macro scale type of phenomena, for which we are actually very familiar with. So I have a huge circle here that is basically talking about a phenomenon that familiar to us, we call the macro scale. And we have all those methodologies available for us to use. Okay. I think everybody is familiar with so-called finite analysis, right? It is, in my opinion, the most successful computational thinking that we have even in the century. And we move further. During my undergraduate study, which is about 30 years ago, I studied for the final year project that I had. I viewed the FEM for nonlinear. Those years difficult for the young people. That was in China that occupy about of this size, maybe really bigger. And they are all big, very, very huge set of computers. And those computers is operating by this kind of a key, you know, the musician, when they play music, it's like the keys. We can use to do that those years. Right? The reading material is also mostly optic type of material. So I did my first research work using FEM. I developed my own codes for nonlinear solid mechanics problem, which was used for simulating a huge bridge. And then, since then, I have been using FEM all the time. Okay. So the FEM, if you're talking about the formulation technology, it is based on so-called weak form formulation. I know about it. Basically, when you have a problem, you know the one that you can solve by analytically, but you have to discretize it. And then you have to actually change the equation in order to be able to build up a discretized equation system. Okay? And that form we call the weak form. In particular, we call the so-called using so-called energy principle. Okay? And then later on, we moved further to develop so-called mesh reasoning. Now, if you use FEM, we have to use element. And then the meshing or the creative model for your problem is going to be sometimes difficult. Difficult, I mean, not so easy for you to do it adaptively. But the adaptation for computation, personally, I believe is going to be very important in the future for people to do more complicated problems. Personally, when I went to Singapore, that is early 1990s, I took a lot of research work with the defense industry. They basically doing simulation like you have a submarine that's in the sea, and then you have some kind of explosives detonating, and that generates a shock wave. The shock will travel within the sea to the structure, which is submarine, and the submarine starts to vibrate. Okay? And not only just vibration, but also could destroy the submarine structure. And then we need to do this kind of a simulation. So in this kind of model, you have simulation of the explosives, simulation of shock wave traveling in the seawater, simulation of dynamics behavior of the structure. And in the process, you have to figure out the interactions between the shock wave and the structure, fluid dynamics and the structure, etc. It was really complicated problem. And once I did that project, it was a huge team of people to do that. We did about 6 years. And after that, there are more projects actually come to see me. Like you have a tank, okay, and then you have mine. The mine gets detonated, and how the mine actually affects the tank. Okay. all those sorts of problems. So if you look at the submarine structure, you look at the tank, okay, only, even if you're just interested in the structural dynamics, the modeling part is going to be very, very challenging. Okay? And if you combine with the interactions of the soils and the structure, and it becomes even more difficult. On top of that, you have material inhomogeneity. Okay? The material is different from part to part, from different substructure in your model. So therefore, we actually moved in study the so-called mesh-free technique. So we come out with a technique that we call the smooth point interpolation method. And that method is actually a little bit different from the formulation of finite element method. And in theory, that uses so-called weak formulation. Okay? We call it W2 formulation. And those techniques further being developed in the sense that when I try to promote the technique as key to people, and then people always have some kind of resistance to use it because everybody did use it. So later on, what I did is try to make this guy as simple as possible. So what I did, I bring in some of the formulation technique theory from the mesh-free technique. And what we do in the finite element method. So I combine these two together and come out with the so-called smooth finite element method. Both methods use a critical operation called smoothing operation. Now, because of that, we have so-called weak statement. And in the later part, I was explaining a little bit about the difference between the weak form and the weakened weak form. But let me just go further. There are also some other techniques, especially when you do so-called fluid dynamics simulation, not structure, fluids. In this case, many people use so-called finite volume technique, okay? And maybe finite difference technique. But all those techniques, finite volume, including this one, this is called the gradient smoothing technique. They are using so-called strong form formulation. Okay? Strong form formulation is basically we have a discretization procedure that applies directly to the partial differential equation without changing the equation into a weak form. Okay? And that worked very well for CFD problem. The finite element method can actually also applicable to CFD problems, but not so many people do that. There's reason for that. Okay? Because when you do so-called weak form formulation, and you have to do a lot of operation, like for example, the integration, because weak form is always dealing in an integral form, so you have to do the numerical integration. But whereas if you just do strong form formulation, you do not have to do that. Okay, so, and also, if you just do solid mechanics problem, and the solid mechanics is governed by partial differential equation, that is symmetric in terms of spatial differentiation. But then the safety problems is governed by Navier-Stokes equations, which is not symmetric in terms of the spatial differentiation. So therefore, even though you bring in the weak form formulation, the system equation that you create is still going to be asymmetric. So we know that if we have to solve an asymmetric system, it's going to be much, much more expensive. So that is why for CFD problem, people often use a finite volume technique. Now, this is only talking about the finite volume technique. They use so-called control volume. Okay, so you bring in so-called physical law of conservation. So then you cut the domain into pieces, then you're making sure the conservation is always being maintained in your discretized model. Now, with this kind of idea, you can formulate all sorts of numerical technique. But there's nothing you need to do is called approximation. So if we're talking about approximation based on element, which is FEM, then we know how to do it. So we basically look at the element with nodes, we just do simple interpolation, then we get the approximation done. But in the mesh-free community, there are all different types of other ways to approximate the function. Okay? So now, in general, if you want to develop a numerical technique, what you do, you cut the domain into pieces. Okay, so it depends on how you're going to do it. In local, you perform so-called approximation using any of these techniques. Okay? And then, with that approximated function, you bring into the formulation procedure that creates a set of system equations. Okay? So now, for all those things that we're doing here, basically is to making sure that when we discretize a system, we get a numerical solution, then we want that numerical solution reliable, okay, converge, okay, so that we can really use it in the design process. So we took so much trouble that is the sole purpose is basically making sure that our numerical solution is usable in the design. Now, after you did all those, then you understand the procedures, how to making sure your solution is reliable. Then we come back to look at this problem that we need to simulate, which is explosive. Now, I mentioned earlier, in the explosive, in the process of the early stage of detonation, there's reaction going on. Okay? So how things reacted, then we need to figure out. Okay? So we come down a little bit, one smaller scale, and that covers in the micrometer range. And in those range, people often use the molecular dynamics technique to do that. Okay? And so then we will think that also, try to use molecular dynamics simulation and to produce parameters or the constitutive equations, also called equation of state. Equation of state is important when you use the so-called smooth particle hydrodynamics technique. And so if you can have some kind of model that gives you all these properties for your material, and then you can just invoke the macro model and do the simulation, achieve whatever you wish to do. Now, when you try to use a molecular dynamics model, then you got to have a critical piece of techniques that is called force field. Okay? You have to have force field. So how to get that one? There's a number of ways. Most people use empirical formula. Okay? So you write, you basically assume that the entire system has a potential. Okay? Then you get perform differentiation from the potential, then you get the forces. And then you just bring in Newton's law, and you evolve your equation, get the solution done. Now, when you come to MD, you look at the equation, actually becomes much more simpler. Okay? So if you get a proper so-called force field, then you don't need to worry about too much about the stability and things like that, because you have the potential is there. So meaning that the system is stable. Okay? So all you need to do is to develop a proper time integration technique, and you're marching forward, and you get your solution done. Now, what we are trying to do is that bring in so-called quantum mechanics technique. Okay? And we go one smaller case down further, and there we build on the quantum mechanics model based on so-called density function theory. Okay? And then we figure out what is the force field has to be. And so at QM model, then there we can actually simulate, take into account the reaction. And that is done by many people. And if you notice that there's a so-called react effect, a reaction, force field considering reaction occurred in the material. Okay? Now, so then we have basically a multi-scale type of population. So if what we planned here can be done successfully, then in my mind I have actually a stable, entire multi-scale simulation technique from the material and all the way to the entire structure that can consist of explosives or structures, okay, can be offset of just like a building. Okay. Now, this is again, I need to maybe talk about a little bit more about the so-called reliability of the numerical solution. I mentioned earlier, if I bring in the quantum mechanics model, all I rely on is density function theory. As long as the density function theory is properly set, then I will be able to actually making sure we'll get a stable solution. Then it's a matter of how big the computer is, and then that limits the model you can simulate. The stability is really relates to the continuum model. In the continuum model, then you have to do things in a proper way. In the finite element method, we know how to do that. Okay, so basically what we do, we create, we cut domain into elements. In each of the elements, we build so-called the shape functions and they use nodal displacement and the shape function and construct a displacement function. Okay? Now that displacement function has to be in the L2 space, basically have to be squarely integratable, and this is basically requirement making sure that the model is bounded. And also you have to making sure the derivatives of the displacement has to be in L2 space. Okay, so this theory is basically called Hilbert space theory. So once this condition is satisfied, then you have a space of the solution, and then you go through a proper procedure, building a weak form, a bilinear form, and a linear form. Then you say, okay, I'm imposing this weak statement. I'm looking for a particular solution that satisfies the weak statement for all the functions from this particular space. So once you get that done, you get the system equation, you solve it. And because of these conditions imposed, we know the stiffness matrix is going to be positive, definite, therefore I will always get that solution, and that solution always be unique. Okay? And we have refinement mesh and making sure that the solution is going to approach to the Now, this works well for finite element method, but then when you use FEM, you may notice that you choose to use a class of elements we call the triangular element for 2D or tetrahedral elements for 3D, and then you find the solution is not always so satisfactory, okay? Especially when you try to look at the stresses for the structure. Okay? And there are reasons for that. Yes, it's because the weak statement usually produce a model. That model's behavior is very steep. Okay? So then you use triangular element in linear interpolation, and that results in a model is very, very stiff, and you can have locking, overly stiff, and all sorts of problems. So therefore, when people use FEM, most of people always choose to use quadratic. Okay, that's the reason for that. Now, but a lot of people want to use triangles, and there are also good reasons for that. Because when you have a complicated geometry, you want to measure. Creating triangular element is the most convenient way to do. Okay? And you can do it almost automatically. Okay? Whereas using other type of element, it is not so convenient. So therefore, we have another piece of theory that we call the weak statement. That is based on G-space theory, which is a foundation for the smooth FEM or smooth point interpolation method. So we make a transition from FEM to the so-called smooth FEM. The G-space theory actually is quite similar as the H-space. If you look at the definition, we use also shape functions, nodal displacement, and the shape functions here may be created based on nodes, not necessarily based on element, okay, because it comes from the mesh fit idea. This function will still be in L2 space, but then we remove this condition. Okay, we are saying that if for this function so created, I'm going to do an integration along the edges of the smoothing domain. And if I do this and square it, and I summarize all these integrated values, squared integrated value, and that value is always strictly positive. Yeah. And then this function will belong to the G1 space. Now, by doing so, I actually didn't perform any differentiation to the functions. What I do is an integration. So, which basically tells that the requirement for the function that I created to build my numerical model is going to be reduced. It's weakened, further weakened. So that's called weak formulation. Now, by doing so, what I be able to achieve is that you can now use triangular element. Okay? So triangular element can work as good as quadrilateral element. So you can move further to do adaptation, to do automatic simulation, followed by propagation and things like that. So therefore, we are thinking that the smooth FEM is a future that we can do a lot of work on it. Okay. Now, in this particular work, we choose to use SPH. And then I have to worry about if I just SPH I mentioned in previous lecture is basically based on strong form. If it is a strong form, I don't have functional space. So there's no way I can make sure the model that I created is going to be stable or the solution is reliable. Then I have to look at other means. In the SPH, it uses so-called smoothing operation. So in the smoothing operation, basically it's a technique for us to approximate the function and the derivatives of the function. And in that process, I try to use so-called smooth functions that is always the diode shape. Okay. Now, and then that approximated function is packed into the strong form formulation. So if I choose a proper smoothing function, and I perform an approximation always locally, and then I can make sure the system equation I create is going to be diagonal dominated. Right? So if you are on the numerical models, you know if I have a discretized system and with a diagonal dominated system, I know I'm going to get something that's going to be reliable. Okay? So now it turns out that the SPH techniques actually works quite nicely for strong form formulation, and that is basically relates to so-called CFD problem. The procedure of doing that is that we just discretize the domain with particles. Okay? And then we use this kind of belt shift smoothing function perform smoothing operation. And then we create systems always based on the Lagrangian formulation so that I can evolve this time properly, allowing all the particles carry the information of the field variables. So it is rather easy for us to use this technique to work with multi-scale modeling. In this technique is not new. Okay, it is actually invented in 1970s. People used in the early stages for astrophysical type of problem is studying the movement of stars. Okay, for those type of huge problems. It is only very recently people use it for so-called CFD problem, and that is governed by Navier-Stokes equations. So the critical piece of technique is basically if I have a function like this and wants to approximate this function, so I multiply a width function, and the width function is something like this, an L shape, and I perform an integration in a local smoothing domain. With this, I will be able to get a value, and that value is an approximated value for a particular particle. And this integral equation can be discretized further in a discretized form or in particle form, and we call the particle approximation. Now, we can do this not only for function, but also for the derivatives of function. You perform mostly a similar technique. So you can actually set up a set of equations to making sure what is the accuracy of the approximation you want to achieve, whether you want to produce the function itself exactly, the first derivative exactly or whatever, from which you set up a set of condition. And when you choose your smoothing function, you are making sure that the smooth function satisfies those conditions, and therefore you are making sure your approximation is appropriate. Now, SPH is used by many people, but we always have some kind of problems. The problems is rather, okay. Now, when you use SPH and you apply it to certain type of problems, especially when you apply to not safety problem but solid mechanics problem, then you have so-called a stability issue. Okay? That is a we call tensile stability. It is rather difficult issue to resolve. What we figured out is that when you try to use this kind of smoothing technique to approximate the function, if you impose the condition too strictly, and the function is not going to be happy, it is not so happy, and then it's going to start to jump and create this instability problem. So what we did in recently is basically we are going to approximate further, not so much insist on the exact reproduction of the function itself. Rather, we are going to insist on the production of the derivatives of the function. Okay? So then we bring in another condition, so making sure that it works well. So with this, we are going to apply this to solve so-called fluid dynamics problems. Now, I mentioned earlier, SPH is good for CFD problems, but then when we simulate, say for example, the effects of detonation of the whole building, so the building is going to break into pieces, right? But they are solids, they are not fluids. So in this SPH, they actually treat this kind of phenomena at all with like as a fluid. Okay, so even though you are the solids, but the flow of the debris is basically forms a flow. And that is the idea that we can use this SPH also for solid mechanics problem. Now here is the Navier-Stokes equation written in the form of Lagrangian form. So I bring in all the approximation techniques so I can actually write this equation in terms of the particles. So in this equation, you do not see the derivatives anymore. All you see is basically summations of the particles and all the particles. So now in this set of Navier-Stokes equation, we need a crucial piece of equation to make it the system enclosed. Otherwise, it's open. Okay. That is the so-called equation of state. Yeah, that is a critical equation that we need. In the past, in order to get the equation of state, many people just make assumptions to get the equation by so-called empirical type of approach. And those are the equations that people used for simulating so-called non-ideal explosives. If it's ideal explosives like a TNT, this kind of explosive, we just use JWL. JWL is basically equation of state to quantify the exploded, the behavior of the exploded gases. Okay. Now, but if you have explosives that is actually mixed with, say for example, gasoline, this kind of burning type of material, then after detonation, you have detonation process, you also have a burning process, and that equation of state becomes more complicated, and that people use so-called JW++ technique. in that process, you have to consider some of the material is not really reacted, some is already reacted. So then you have sort of a mixture of reaction in your entire domain. So that is why it becomes a little bit more complicated. So you have equation of state for unreacted explosives and reacted explosives. And then when you are simulating the events that is happening, you basically combine these two together by this so-called rule of mixture. And then in which you always have a so-called burning fraction. So meaning how much the percentage of the material is burned, how much is not. The burning fraction is controlled by another differential equation. So now you have a scheme. You evolve with all the particles, then evolve with time, bringing the so-called equation of state. And in each of the process of simulation, you always have the burning fraction function is evolved in the process. And then therefore you can do the simulation. So we did that using this so-called empirical formula. We built a model. The model is we call the ANFO material. It's non-ideal type of explosive. That's built inside, and oh no, this is just a cylindrical type of material. So, but on the surface, a layer of particle, I give an initial velocity. So, simulating a detonation processes, you have explosive impact and see how it is detonated. So, this is a process. This is the early stage at the 25 microsecond. Here shows the velocity in the x direction distribution. So this part you see is already detonated. And so once the time goes on, the detonation goes further and further. And here it looks like the reaction rate. So you see here actually there was a layer of particle gets reacted, and the reaction goes further and further. I think I should have a animation. Why the animation is no, it's supposed to be animation. So basically shows the process how we get detonated. Yeah, this is reaction rate distribution changes with time. Oh, here. Here is another model. What I have is a explosive inside, cylindrical. On the surface, I have a copper cylinder that holds in this explosive. Okay. So you see the detonation. So everything, this is, although the casing is a solid material, then it gets fragmented into pieces. And this is a comparison with the experiment and the simulation. We are comparing this the displacement. Basically, this can be measured. You perform a detonation, you take a picture of it with the time, so you see the expenditure of the radius of the cylinder with the time, and you compare with the simulated results. And this is a charge, we call it shaped charge. At the initial stage, you have this kind of shape, the explosive, and then you detonate at this particular point, and then you have casing material here, and then linear material here. So after detonation, the explosive actually force the metal to form a very fast traveling jet, and that jet will be able to penetrate the steel there and the further. Okay, and this is simulated results. Now, so we see the SPH actually work for this type of problem to a certain degree. But then the EOS that we used is from empirical. So what we need to do now is bring in so-called molecular dynamics model and use MD to produce EOS. So this is a part here. So we built a MD model for an explosive called HMX. And this is the material composition. And we use NUMS to do the simulation, in which we bring in so-called reacts effects, okay, to provide the force field function. And in the first model, what we are considering a situation is that I have a piece of crystal, which is the HMX crystal. I compress it into about 30% in volume, okay, compress it. And then we maintain at that state. This is MD simulation, so I have all the model being created. So I maintain, I look at the equilibrium, I let the system being equilibriumized, keep it for a 1 picosecond. Okay? And using this so-called NB, so I keep the volume and the energy unchanged, and then let it to stable. Once it is stabilized, and then I release the system, meaning I'm not going to confine its volume anymore. So the whole thing just go up. Okay, so that trying to simulate the explosion process. So the reaction FX is quite complex. And if you want to know detail, it's going to be read in this paper. The second model we built is use a lot of items. It's about 1,792 for beta HMX. So we use a different model and a different way or different assemblers to simulate the process. Why we do this is because we don't really know which one actually simulate the best to the explosion process. And this is the one we use so-called anti-shook ensemble, which is the one that I mentioned earlier, compress it first and release it. So we look at the change of the density with the time. In our study, we tried to use different time step to see whether the time step that used in the MD model will affect the solution or not. In this case, it is not affecting. So we carry on to look at the temperature change. So once detonated, the temperature jumping up like this, and with the time, and this is comparison when we use a different time step to do the simulation, and quite close also. And now when you do the so-called releasing, actually there's a lot of details. Okay, so you have cylindrical type of explosive. When you release it, you have a number of ways to do that. The first, maybe I just confine the cylinder and all the circumferential surfaces, but I allow the x direction to be free, so the mercury can actually go all in one direction. Or I can actually allow everything being free, so therefore the explosive goes to every place in space. So when we observe the temperature change with the time, now we see that actually depends on how you do it, we will have this kind of differences. So it makes things a little bit more complicated. Complication basically, we do not really know which is the best way for us to actually simulate the process. So we do both of them. Look at the pressure against the density, which is the equational state that we want. And then we perform the simulation, we get this kind of relationship using two different ways. And then this equation of state is compared against the experiment. Okay? So we found that there's a discrepancy um, um, it's close, but it's not to what we want. Okay? So we have to actually move further to see what is going on. So our further study is like this. We look at the material, which is HMX, and then we fix the temperature at 300 degrees K. And then we use a different way to do it. We built a sort of DFT model, which is quantum mechanics model. Then we have a curve like this. And so this, because we fix the temperature at 300 degrees, so there's no burning occur. It is purely compressed out piece of crystal. Okay? And then this is the DFT solution. And this is the experiment from this guy. Okay? Actually, it's reasonably good match. But then we bring in this MD, which is this one, MD solution. I get a curve like this. Now, at early stage, it looks good. But then later on, it doesn't really match very well. Now, remember that in our MD model, we actually use the react effect, meaning the force field actually has a reaction occur in the process. Although in 300 degree K, it's not supposed to have any reaction, but somehow this reaction effect is there. Why we know that? It is because when I use this result here, this result is getting from a experimentally determined US. So, but in the experiment, the things actually is detonated. During the experiment, is detonated. So therefore, this experiment actually contains the effect of the reaction in the process. So the MD does somehow shows that the reaction is being taken care of, and that is why it departs from the DFT solution. So we moved to further. We still couldn't really figure out how to get it done. So we further look at the influence of the temperature. Remember I mentioned about this empirical formula for the JWL. In the JWL equation, actually, they have a particular term taking care of the temperature. Okay, so so in the MD model, we can always do that. So we can actually assume a certain temperature. So we let the model evolve and always fix until it is stabilized at that particular given temperature. We can do that. So we set up temperature 1,000, 2,000, 3,000 to see how the curve actually changes. So if we put all the curves together, and this is MD solution, so when the temperature changes, actually the equation of state changes. Okay, so further confirm that, okay, that equation basically taking care of the reaction and the temperature does affect the behavior. But when we look at this JW, which is getting from the empirical solution, it actually doesn't change that much. So there's still some discrepancy there. We don't know how to get it done. In the MD model, we can actually go further to look at the product of the reaction. Okay. Here shows three pictures with different compression rate. So this is compression 1.1. If you look at the paint, meaning that I compress it 10 times, okay, the material is compressed. So this is 1.1, this is 2, and this is 10. So you see that if I compress very heavily, so the reaction actually completed quite early. The final product, the number of products is stabilized after a certain time. So basically this allows you to see the gas product that is being actually generated through the reaction process. But then which increase the temperature, and this situation gets more complicated. We still analyze the data, but we haven't been able to actually conclude what should be done for this generation of the EOS at this moment. So the conclusion so far we got is that we still do not know exactly what to do, but we somehow think that in comparison with the experiment done in the macro scale, if we just bring in these reaction effects and fix that the temperature at 300 degree K, seems to give me a good result. But it's not right. So we are still struggling on this part. So I assume that is right, so we can do a further simulation. The simulation is done against the cylinder, cylindrical explosive, and I compress it at the end, and then you see the shock wave, because the reaction, the shock wave is generated, the shock wave starts to propagate. So if I look at different time, you will see all different change in terms of the pressure. So this one is, okay, so you maybe look at this one. So this is, is when you look at, I think it's 10 microsecond. So the shock wave basically, shock front is here. Another 10 microsecond shock front comes here. So the time goes on, so your shock wave front is propagating a non-one-dimensional explosive. Difficult to compare with experiment, but in the experiment we can always measure is the peak pressure. The peak pressure is this peak, this line here, is measured by the experiment. So this numerical solution is basically quite close to that part. The blue curve is doing the same simulation, but I use traditional EOS. It's not the one that I get from the MD. Okay? There are some discrepancies here, which we do not know. And we also look at the density change in the one-dimensional explosive. Velocity change, basically quite a similar thing. So, not ideal to what we expected, but then I think this is working. The MD with SPH is working. So we just carry on with the simulation, and then this is supposed to be animation. So maybe just look at this. So this is the initial stage, the detonation goes on and on and on. So this is the final stage. Oh yes, here must be the process. So detonated at the left edge, and then propagates. So this is a free coupled MD and SPH model. So we, as I mentioned, we still really have an idea how to fix the MD. The EOS is not precisely correct, so we are still working on it. And we are thinking maybe we go back to look at this quantum mechanics model to see whether this reaction effects that created is really appropriate for this type of problem. And so this is still ongoing. I'm sorry that my talk, the conclusion is not successful conclusion, but I think for this kind of symposium, probably people should represent something even if it's not so successful. And in reality, I believe, whenever you get something good, you must did a lot of things is not so good, right? So with this, I conclude my talk, and then if you have any questions, let's discuss. Thank you.
Right, thank you, GR. Sure you can be able to answer questions.
Go ahead.
I'm not sure if I understood everything correctly, but I have the impression that you are finally aiming to couple the atomistic scale simulations with the
SPH.
SPH. You are not at that point yet.
No, no. This couple is done.
Okay.
Is we are suspect that the US we get from MD is not really trustworthy at this moment.
But for that coupling to be important, the fluctuations of the properties at a molecular level must be important for the macroscopic, for the more large-scale behavior. Otherwise, you could compute the average properties from a purely molecular scale simulation, and then use these average properties to simulate in a more large scale.
Yeah.
Is that the case? You really need the fluctuations that are happening in a molecular scale to...
Okay, the model goes like this. You have all the particles for explosive and whatever the material casing, for example. And this is discretized in particles. So when the detonation goes on, you can imagine the particle is all over the place. So the MD sits on each of the particles. Okay. So in let's say I look at one particular particle. So
just
for one
particle. In the best case, a particle in that case is one of these detonation experiments, or what?
What is really a particle?
What's really a particle when you're...
The particle is a material.
It's a material particle.
It's a material particle.
And that,
SPH always a material particle.
yeah.
Yeah.
But that does not correspond to an atom of your molecular. That's the point. What is the scale?
Yeah. So that particle is physically it's actually big one.
Yeah.
It's not the atomic scale. But then that particle behave, I mean, in terms of the EOS, the equation of the state. Then we are assuming another MD model for that particle. Because at that particle, we know what is the temperature there, what is the pressure there, and the energy number there. So then we can build an MD model. And we run that model, that is stabilized, and then we will get the equation of state, basically for giving any fixed volume, I want to know what the pressure is. Okay. So from there, I run my MD, then I know the equation of state for that particle. There are a number of ways to do that. We do not know which way is the best. As I mentioned earlier, we can actually compress the material to a stage and then release it. By doing so, allow us just do one MD, dynamic MD1. I will get my equation of state for all the different volumes. Another way is for each of the particles, I run equilibrium simulation and MD simulation, making sure it is stabilized for different volume and given the pressure. So I can show both of the cases. The first one is not so satisfactory. We're trying the second one is also not so very good. Still struggling. Yeah.
And how do you take care of the inhomogeneities of the particles? So that particle, it's a mesoscopic set of atoms.
Yeah.
You know that part. But then there's another part. There's
Right.
another mesoscopic
Right.
size
Right.
system.
Right.
How do you take care of this? They are not when you
No.
detonate. They're under different.
They're all different. So we bring in so-called JWL plus idea. So for any of the particle, we basically assume you have two types of material. One is reactive, another one is not reactive. But the ratio of the so-called the Benny fraction is different from particle to particle. So the particle here is fully burned, particle there is not burned at all. So to actually represent this status for those kind of material, that's really
The boundary conditions of each mesoscopic particle need to be used for calculation of the simulations were really coupled. We would need to update the boundary conditions of each mesoscopic particle with the
Yeah, that is a part we suspect. We couldn't get it precise in the US. It is because we are assuming a particular ensemble. Okay, but in reality, it is not. It is some kind of combination. I'm thinking probably you can do a NDT or maybe do a NPT. And this US must be between these two. That's what I suspect. But we will not know exactly for sure yet.
Maybe some sort of free boundary condition for each
Yeah.
part.
Yeah, so free is corresponding to the pressure is fixed, basically, NP, or volume fixed. So if I go back to the continuum mechanics, I know really well. If I want to estimate one modular, I can fix the volume, and then I can fix the force. I know this is going to give me either upper bound or lower bound. So by the same argument, for the NP, I'm foreseeing this kind of ensemble has to be somehow mixed together. It's not so simple as we did just now.
Further questions? Questions? No, let's thank the PR once more, and we are sure that